Good morning. Welcome back to our physics class. Today, our topic of discussion is radioactivity. I think you had studied the basics of radioactivity in your plus 2 classes. We are starting our topic radioactivity. You can see a symbol on the slide, and this symbol written caution represents the presence of a radioactive material in a particular region. Moving on to our topic radioactivity. The phenomenon was first discovered by a French scientist, French physicist Henri Becquerel in 1896. He did his experiments with pitchblende, which is an ore of uranium. He observed that pitchblende emits certain radiations and it can affect the photographic plate even when the plate was in a light-proof package. So he observed that the pitchblende emits certain radiations and he named that radiations as Becquerel rays. Later on, Marie Curie and Pierre Curie in 1898 discovered both polonium and radium. And they found that this polonium and radium are also the strong source of emission of Becquerel rays. And they started to study the properties of the radiations emitted by such nuclei. And they revealed that these radiations consist of helium nuclei, electrons, and high energy photons. And these radiations are produced due to the disintegration of nuclei. So they defined radioactivity as the decay of atomic nuclei with the emission of helium nuclei or electrons or high energy photons. The helium nuclei are called alpha particles, the electrons are called beta particles, and the high energy photons are called gamma particles. So we can define radioactivity as the spontaneous emission of radiation from the nucleus of an unstable isotope. So the unstable nuclei undergo disintegration and produces certain radiations like alpha rays, beta rays, and gamma rays. So we can define radioactivity is the process whereby unstable atomic nuclei release energetic subatomic particles. Here the subatomic particles are helium nuclei called alpha particles, electrons called beta particles, and high energy photons called gamma particles. And we had already said it was first discovered by the French scientist Henri Becquerel in 1896, after which the SI unit was given the name of the scientist Becquerel. So there are two types of radioactivity. First one is natural radioactivity and second one is artificial radioactivity. What is natural radioactivity? The radioactivity exhibited by naturally occurring elements is called natural radioactivity, and it takes place spontaneously without any external cause, or we can say no external agent is needed for natural radioactivity to occur. It's a spontaneous process, and this radioactivity is exhibited by nuclei with Z greater than 82. For example, radium, actinium, polonium are the elements that undergo natural radioactivity. So whenever a parent nuclei undergo radioactivity, a new daughter nuclei is formed, and such ultimate product of natural radioactivity will be lead with Z is equal to 82. That means the ultimate product of natural radioactivity is lead with the atomic number 82. So we know that radioactivity is the decay of unstable nuclei. So this unstable nuclei undergo decay and form lighter nuclei, or this unstable nuclei will undergo radioactivity in order to attain stability. So the ultimate stable product of a natural radioactivity will be lead with the Z is equal to 82. So all the nuclei with the Z greater than 82 are unstable, and hence they undergo natural radioactivity. Now, what is artificial radioactivity? We had said that natural radioactivity occurs in a unstable nuclei. Now, in artificial radioactivity, we are converting stable nuclei into unstable by bombarding them with fast moving particles. So, stable nuclei are made unstable by bombarding it with fast moving particles. So they will become unstable because they had gained energy from the bombarding particles. So getting high energy means they are losing their stability and becomes unstable. So this unstable nuclei will undergo radioactive decay. And this type of radioactivity is called artificial radioactivity, in which radioactivity occurs by artificial means. So here what we are doing is that stable nuclei is made unstable, and this unstable nuclei will undergo radioactivity. So we need an agent or external trigger to start this radioactivity. So this radioactivity is known as artificial radioactivity. Now, if the artificial radioactivity persists or exists long after the bombardment with fast moving particles ceases, such artificial radioactivity is called induced radioactivity. The phenomenon of artificial radioactivity that persists long after the bombardment with the fast moving particles ceases. So we are making the stable nuclei unstable by bombarding it with fast moving particles. So if we have stopped this bombardment and the radioactivity continues for a long time, then we can say that such radioactivity are known as induced radioactivity, which persists long after the bombardment stops. So we can just have a look on the differences between natural and artificial radioactivity. First one, natural radioactivity, we know that it is spontaneous, and artificial radioactivity is not spontaneous since it needs a bombardment with the fast moving particles. So it's not spontaneous. Now second difference, natural radioactivity is uncontrolled, so that it cannot be slowed down or it cannot be accelerated. Since artificial radioactivity is by artificial means, we can control the artificial radioactivity by controlling the speed of the bombarding particles. Now, natural radioactivity, we had said that natural radioactivity is shown by the nuclei with a Z greater than 82. That means it is shown by heavy elements. Now, artificial radioactivity can be induced even in lighter elements also. So these are the differences between artificial and natural radioactivity. You can include the definition of natural radioactivity and artificial radioactivity in this column. Now, what is the cause of radioactivity? We know that unstable nucleus undergo radioactivity. So, instability of nucleus is the main reason for radioactivity. And we had studied the binding energy curve, isn't it? And we know that the nuclei with a high atomic number have low binding energy per nucleon. So when the binding energy decreases, the nucleus will be unstable. So the nuclei with high atomic number will have low binding energy per nucleon, which makes the nucleus unstable. Now the third reason is, think that if the nucleus contains more number of protons, what happens to the binding energy? If there are more number of protons inside a nucleus, the Coulombic repulsion between the protons increases and it will give rise to the instability of the nucleus. So these are the three reasons for the cause of radioactivity, that is instability of nucleus, low binding energy per nucleon for nuclei with high atomic number, and the increased Coulombic repulsion between protons in the nucleus. Now let's have a look on the experimental setup of the radioactivity, in which a sample of radioactive element or radioactive substance, let it be radium, is placed in a small cavity drilled in a lead block. So you can see a lead block here, and inside that lead block a small hole is drilled, and inside that small hole we are placing a radioactive substance, radium. Now radium is a radioactive substance, so it will emit the radiations. In order to know, or in order to make the analysis of these radiations, electric field is applied by two plates as shown. So the electrically charged plates are given in their way, and also they are allowed to fall on a photographic plate. So here you can see the three radiations coming out. They are alpha rays, beta rays and gamma rays. Now alpha rays, you can see the alpha rays are deflected slightly towards the negative plate. That means alpha rays are positively charged. Now beta rays are deflected towards the positive plate. That means beta rays are negatively charged, and gamma rays goes undeflected to the photographic plate, or gamma rays remain undeflected. That means gamma rays are neutral. And this is the experiments which we had done with the help of electric field. and they got the same results when these radiations was subjected to the action of a magnetic field also. From this we can conclude that alpha rays are positively charged and beta rays are negatively charged particles and gamma rays are neutral. Now let's have a look on the differences between alpha, beta and gamma particle. We had already said that alpha particle is identical to the helium nuclei and a beta particle is a high speed electron, or it can be a positron. Now what is positron? Positron is the antiparticle of electron having same mass as that of electron but opposite charge. Now a gamma particle is a photon that carries energy in the form of electromagnetic waves. So the first point is to identify each particle. That is, alpha particles are helium nuclei, beta particles are electrons or positrons, gamma rays are electromagnetic radiations or photons. Second point regarding the charge of these particles. Alpha particles are positively charged particles. Beta particles, since there are electron and positron, electron is negatively charged and positrons are positively charged. Now gamma are neutral particles, and the third property is atomic number. So what happens when an alpha particle got released from a nuclei? We can write a helium nucleus as He24. That means the atomic number got reduced by 2 when an alpha particle is released by the nucleus. So think that X is a parent element having atomic number Z and mass number A. If an alpha particle got emitted from this parent nuclei, what will be the atomic number of daughter nuclei? We know that helium is having atomic number Z is equal to 2 and A is equal to 4. So if this helium nuclei got emitted from the parent nuclei will have an atomic number Z minus 2 and mass number A minus 4. Now what happens when a beta particle got released from a nucleus? Atomic number of the element is increased by 1 unit when a particle is released. We will study in detail both all the decay processes like alpha decay, beta decay and gamma decay in detail in the next class. So you just have to note that atomic number of an element is increased by 1 unit when a beta particle is increased. Now atomic number is not affected by gamma emission. Now the fourth point is, whenever a alpha particle or beta particle is emitted from a parent nuclei, we will get a daughter nuclei because the atomic number changes in the case of alpha as well as beta decay. So the emission changes the chemical element when an alpha or beta particle is emitted. But in the case of gamma decay, there is no change in parent nuclei. Now the next point regarding the penetration power. Penetrating power is more for gamma rays and very less for alpha rays. Now this penetration power is inversely proportional to ionizing power. That means ionizing power is greater for alpha particle and lesser for gamma particle. Now let's say about the speed of these particles when they get emitted from the atomic nuclei. Speed of alpha rays is about a tenth of the speed of light. and the speed of gamma particle is about 90% of the speed of light. Now gamma rays are having the velocity equal to the velocity of light. And we had seen in the experiment how these particles got deflected when electric field is applied. And the same results will be available if we are keeping this in a magnetic field also. That means we had seen that the alpha particles had deflected towards the negatively charged plate, isn't it? That means they got deflected by electric field. So the alpha particles are attracted by electric as well as magnetic fields, and beta particles are attracted by both the fields, and we had seen that the gamma rays had gone undeflected. That means gamma rays are undeflected by electric and magnetic fields. So these are the differences between alpha, beta and gamma particles. So we had studied what is radioactivity, and we had seen what is natural radioactivity and artificial radioactivity, what is the cause of radioactivity, and what are the radiations emitted from a radioactive nuclei, what are the properties of these radiations. Thank you.